Okay, good morning, everybody. Welcome back. The plan for today is to start talking about chapter 4, which is basically about contact forces, forces of things that are in contact with each other. Contact forces are not fundamental forces. They're made up of lots of forces at the microscopic level that are. So we'll have to go take a microscopic view of the world to see how this actually works. So today we're going to be talking about contact forces. And contact forces are interesting because they're really different from everything we've done up to now. Up to now, we've modeled everything from protons to galaxies as point particles. So when we talk about the force exerted by the Earth on a spacecraft, we're actually modeling both of these things as points at their centers. So what we need to do with contact forces is because contact forces involve deformation, when things touch each other, they actually can deform. And so we need to have a microscopic view of what's happening. Contact forces are usually divided into two kinds. We'll see that there's tension forces, which involve pulling, and compression forces, which involve pushing. And we'll also see that friction is a kind of contact force. We'll have a mechanism for understanding friction by the end of this. And the microscopic view, so we're going to have to go down to the atomic level to look at matter to see what's happening. So that's going to be our mission for the next 2 lectures. Now, let me try to convince you that there's actually something here that's a little mysterious and needs to be explained with contact forces. We're going to consider a really easy problem. There are several forces acting on this person. So the Earth is pulling down. And the person is not accelerating downwards. So presumably the floor is actually pushing up. By the momentum principle, these two forces have to be equal and opposite. So we can calculate the force that the floor is exerting on the person, right? Because if, so the net force is just the gravitational force due to the Earth plus the force by the floor. And we can worry about magnitudes here. So we can say that the magnitude of the force, the gravitational force, is going to be equal to the magnitude of the force by the floor. And let's say this person is 60 kilograms. So this is 60 kilograms times 9.8 newtons per kilograms. That's about 10 newtons per kilogram. Is going to be equal to the force by the floor. And that's equal to 600 newtons. So the floor is exerting a force of 600 newtons upward on the person. Okay, very basic. Now suppose that the person goes away and we have a raccoon standing here. And the raccoon weighs 10 kilograms. So we know that the floor exerts an upward force of 600 newtons because we determined that already. but the Earth is exerting a downward force that's less than that. So F gravitational due to the Earth is about 10 kilograms times 10 newtons per kilogram. So it's about 100 newtons. So that the net force should be 600 minus 100 is 500 newtons upwards. And therefore, the momentum of the raccoon should change dramatically in the next second. We're going to get a change of 500 kilogram meters per second, and the raccoon is going to fly upwards, right? That, however, is clearly not what happens. So why doesn't this happen? If the floor exerts a 600 Newton upward force on the human, why doesn't it exert a 600 Newton upward force on the raccoon? A floor is not a sentient thing. It doesn't know that a raccoon has less mass than a human. So how does the floor figure out what to do? It's a floor. It looks like, since we know that the raccoon, we know that the raccoon experiences a downward force of 100 newtons, that in fact the floor must be exerting an upward force of 100 magnitude 100 newtons. And so the floor changes the force it exerts on the object in contact with it, depending on the mass of the object in contact with it, depending on how hard it's. Yeah, so that's right. The floor adjusts its force, but how does a floor do that? And that's the reason that we're going to need to go down to a microscopic level and look at what's happening with a floor. Now, we all know, because we've taken chemistry, that matter is made of atoms. But we probably haven't talked very much in chemistry about how they're put together to make solids. So what this is, these are images taken by a scanning tunneling microscope. There are two kinds of microscopes now that allow us to image matter, solid matter at the atomic level. So this is a solid surface. It's an image from a scanning tunneling microscope. You get the same kind of images from things called AFMs, which is an atomic force microscope. The way an atomic force microscope works is very cool. You drag a very teeny tip across a surface, and as it goes across the surface of an atom, it actually experiences a force, and you measure the force on the tip, and you can actually get an image of the surface. So these are two images that were taken of a very flat surface. And you can see that you can actually see the atoms. They're there. And the thing that really stands out is that they're arranged in a very regular array. A very regular array. And this regular array, a 3D regular array of atoms, is called a lattice. the word we use to describe it. But we're only looking at a surface here, so what's going on in the rest of the material? Well, what's going on is that these atoms are arranged in a regular array. They might look, it might look something like this is kind of an idealized rendering of a particular, this is a rendering of a particular regular array. This is called a cubic arrangement. And you can see that the atoms are arranged basically as if they were at the corners of a cube. There are more complicated arrangements where there's an atom in the center of the cube, or there are lots of other arrangements. But this is the simplest possible one, just atoms at the corners of a cube. And we're going to use that for our model just because it's actually the simplest thing to work with. Now, these things aren't just sitting there, though. They're actually bonded to each other with chemical bonds. In a model that physicists have used very productively for what a solid looks like is that we can consider the atoms, these massive atoms, as little hard balls that are connected to each other by springs. What are the springs? Well, the springs are actually just the covalent chemical bonds. These are all images from the textbooks, so you can find them there. They're covalent chemical bonds that connect the atoms to each other. And in this model, what we're saying is that the ball represents the nucleus and the inner electrons. Now, almost all the mass of the atom is in the nucleus because protons and neutrons have masses 1,000 times greater than electrons do. And that this electron cloud that forms the chemical bond is actually represented by a spring. So the key of this model is that we're going to model these chemical bonds between atoms as if they were spring-like. Now that turns out to be a really good model for a chemical bond. And to work out the details, what you need to do is it's a complicated calculation because you have to take into account that all these little particles have quantum mechanical properties. Particles that are really small behave differently fundamentally than particles that are objects that are macroscopic. But the basic idea is this: there's some equilibrium distance here between these two atoms. If you stretch the spring and pull them apart, stretch the bond, then they're pulled back together. Whereas if you try to push them too close together, they're pushed. They try to get back to this equilibrium distance. And in fact, this is a very spring-like force because it's proportional to the stretch of the bond. So a spring is a really good model. Okay, so this is so why am I not drawing the electron clouds overlapping? Okay, this is a very idealized sketch, and sure, the electron cloud is probably going to look, I don't know, something like that. But for our purposes, this is good enough. So Seth, you've got it exactly right. When you stand on the floor, you're compressing these bonds, and these atoms don't want to be pushed together, so they're exerting a force back on you that is proportional to the amount of compression. So this turns out to be a really good, we call this the ball spring model of a solid. And this model gives us a way to think about forces that involve stretching these springs. For example, if instead of standing on the floor, the person was hanging from a cable, then that cable would stretch. But if the raccoon hung from the cable would stretch a little bit less. Now, obviously, these stretches and compressions are not very big, because we would notice if the floor sagged every time we stood on it, or if ropes stretched significantly since we hung things from them. But they're enough. And there are an awful lot of these bonds getting compressed or stretched these tiny distances, and they add up to very big forces. So our goal for this lecture is to find out the characteristics of this spring-like bond and objects made from them. So describe characteristics and in particular, since we're going to model them as springs, we should be able to get a spring stiffness for a chemical bond. So that's our goal. So, so if we consider, we're going to consider tension forces. So we're going to consider a situation kind of like this one, just for concreteness. If we have, so this is our representation of a wire, a metal wire, and just hanging there. And this is a representation of the wire with a mass hanging from it, exaggerated for effect. And so we're talking about here stretching these chemical bonds, and we want to find out how much they stretch and therefore what their stiffness is. Now, there's some counting involved, because if we have a wire, wires are three-dimensional, they're not one chain of atoms. And so what we've got is this wires that look like this network, this lattice of balls and springs. And so if we take a bottom view, we're looking up in the wire. Here's the edge of the wire, the top of the wire. The bottom of the wire has more than one atom in it. And so we have to do a little geometry and a little counting to get. So our basic plan is something like measure the stretch of a wire with a known force. Figure out how many springs are in the wire. Chemical bonds. And from that, we can get the interatomic spring stiffness. For one chemical bond. And this should be different for different materials. We should get different numbers for very stiff metals like iron, or we should get a much lower number for really soft, stretchy things like lead, for example. So it should depend on the properties of the actual material. And so what we're going to do this is we're actually going to do some counting. And the first thing we need to figure out is, in order to figure out how many bonds are in the wire, we basically need to figure out how many atoms are in the wire, because there's going to be a bond between every two atoms, right? And so what we need to do is figure out in some piece of metal here how many atoms are in this piece of metal. And to do this, we need to relate, we can start from the density of the metal, and then we're going to relate this to the size of an atom. So we're going to go from the density of the metal to the size of an atom. And we're going to say that in this regular array, because they're in this cubical array, every atom occupies basically a cubical space, whether there's electron density in there or not. And the diameter of the atom here is basically what we're after here. So we want to get the diameter of an atom. And that's going to be useful to us because the diameter of the atom is related to the length of a bond here. So if we look here, this distance is going to be d, the atomic diameter. And so this distance is d over 2 the radius. This distance is d over 2 the radius. So the length of the bond is equal to the diameter of an atom in this array, right? Okay, is that clear what we're doing? All right. So basically what we're going to do is here's our plan. We're going to work with copper. And copper has a mass density of 8.94. It's usually given in grams per cubic centimeter. And so our plan is, when we're trying to get an atomic diameter d here out of this, what we're going to do is we're going to find the volume of one atom. And if we take the cube root of that, that's going to give us the length of one of the sides of this cube, d. So the plan is to go from density, which in kilograms per cubic meter we need to convert. Then we're going to get the number of atoms per cubic meter. And then we can invert that to get cubic meters per atom, and then we can get the side of one of those sides of the cube, basically. So the first part is just to convert to grams per cubic centimeter to kilograms per cubic meter. So we have 8.94 grams per cubic centimeter, and this going back to your chemistry conversions of units, we have 1 kilogram per 10 to the third grams. So grams should cancel. And then we have 100 centimeters per meter. So we're going to have 100 centimeters, that quantity cubed per cubic meter. So that should get rid of our centimeters cubed. And if we work this out, we get 8.94 times 10 to the third kilograms per cubic meter. Now, how many atoms? Well, we have 8.94 times 10 to the third kilograms, and we know that 1 mole of copper is 0.064 kilograms, 64 grams. And then we know Avogadro's number, so we know there's 6.02 times 10 to the 23rd atoms per mole, which gives us 8.41 times 10 to the 28 atoms per cubic meter. So what we really want is we want cubic meters per atom. So 1 over this number, 8.41 times 10 to the 28 atoms per cubic meter gives us 1.189 times 10 to the minus 29 cubic meters per atom. And so the diameter, the diameter of the atom, the side of this cube is D is the cube root of this. 1.189 times 10 to the minus 29 cubic meters. And that gives us about 2.28 times 10 to the minus 10 meters. This is the diameter of a copper atom. Now, I'm not sure if you have a sense of the size of atoms. What does the size of an atom mean? Well, we're talking about the diameter of the electron cloud around an isolated atom, right? But this is about right. So the diameter of an atom is on the order of 10 to the negative 10th meters. Do you know the diameter of on the order of magnitude of diameter of a nucleus, an atomic nucleus? Okay, a nuclear diameter is much smaller. You're close, Alexander. So it's on the order of 10 to the minus 15 meters. That's on the order of the radius of protons and neutrons. So it's 10 to the 5th times smaller. So in our picture, the nucleus would actually be an invisible dot, given the. It's not a matter of memorizing particular atomic diameters or nuclear diameters. It's a matter of knowing orders of magnitude, which is actually a very useful thing. It's like knowing that the speed of light is 3 times 10 to the 10th meters per second. 3 times 10 to the 8th meters per second. So angstroms are not used in SI units. An angstrom is 10 to the negative 8th centimeters, but we're just going to talk about meters here. So now we know this. And so we know roughly how long one of these bonds, so this is in our ball spring model, this length here is about 10 to the negative 10th meters, the length of a spring. So it's clear that any individual bond isn't going to stretch or compress by very much, but when we have a lot of atoms, and so that can add up to, if they all stretch, we're going to get significant deformation. But going back to this picture, we have some other issues here, because we have, first of all, we have lots of springs in a chain. So here's our chain of springs, and we need to be able to relate the stiffness of a whole chain of springs, which is what we're measuring if we hang weights on the end of a wire, to the stiffness of one spring. So we need to relate stiffness of the chain to K sub S for one spring. So let's think about how this happens. So first of all, with a single spring, how would we measure the spring stiffness? The simple thing to do is to take a spring. We know its relaxed length. Yeah, exactly. How much it stretches under a certain force. That's right. So we hang some mass on it. We look at the stretch. And so springs, we've been talking about springs. So how much it stretches when we apply a certain force. And the easiest way to do it, apply a known force, is just to hang a known mass on a spring, in which case we can draw a diagram of the forces here. So here's our mass, M. We know that the Earth pulls down with a force in the y direction of minus M times G. We know that the spring, if the mass is hanging motionless, the spring must be pulling up with, so this is gravitational, that's the spring force, must be pulling up with a force of K sub S times S in the plus Y direction. And so therefore, we can actually solve for K sub S. So if we have force by the spring in the Y direction is equal to force by the gravitational force in the Y direction. So we have K sub S times S equals M times G. And so the spring stiffness we would just get from the weight of the mass divided by how far it's stretched. So all we have to do is measure this. So if the block, let's say the block had a mass of, let's make our life easy. Mass is 2 kilograms. And the stretch was half a meter, say. Then we'd have the spring stiffness was 2 kilograms times, let's be approximate here. We'll use 10 newtons per meter for the Earth's gravitational field, divided by half a meter. So we'd have, what, 40 newtons per meter? 2 divided by 0.5 is 4, yeah. Okay, so there's not much to it, right? But let's think about what's going to happen if we have, so that's easy, but what if we have 2 identical springs hooked together? So here's one spring, but what we do is we hook 2 springs together, and we know that that one's stretched some distance s. What's going to happen when we hang a block on this thing? Let's think about what's going to happen here. So okay, so here's our question. We hang a 1 kilogram mass from a spring, which stretches 0.4 meters. And now we're just going to string 2 of them together end to end like we just drew here. And the question is, how much is that chain of springs going to stretch? Try to picture this in your mind. Maybe even drawing a picture would help. Okay, so we have far from a consensus. The majority do say 0.8 meters. So let's see if we can sort of work out what would happen here. And I think the thing to do is to actually draw a picture here. The picture is something like this. If we have one spring with the length L0 and we hang our mass on it, we have this stretch S. Now if we have 2 springs with a mass on it, let's consider the bottom spring. So here, so the bottom spring is supporting the weight of this mass. So it's going to do exactly what it did before. Okay, it's going to stretch by an amount S. The top spring is supporting the weight of all this stuff hanging below it, the spring, and we're making the assumption that the masses of the springs themselves are negligible here. So it's supporting the mass of the spring, but also supporting this bottom thing. So it also is going to stretch by an amount S. So the total stretch is going to be 2 times the original stretch. So in fact, it would stretch twice as much. Does that make sense? Okay, assuming it makes sense, you can try this one. So actually, let's go back here. What does that tell us about the spring stiffness? So 2 springs in series end to end stretch twice as much for the same mass. So it looks like actually the effective spring stiffness, so here the effective spring stiffness is actually so of the whole chain. We got the same mass, but we got twice the stretch. So this would be the effective spring stiffness would be something like 2 kilograms times 10 newtons per kilogram. Sorry, that's newtons per kilogram. But now it stretches 1 meter. So in fact, the effective spring stiffness would now be 20 newtons per meter for 2 springs. The stiffness is actually lower, right? What would happen if we had 3 springs? It stretches 3 times as much, right? So we get 3 times the stretch. And the effective spring stiffness, effective, let me write out effective so you can. The effective spring stiffness for 3 springs, 2 kilograms, 10 newtons per kilogram over 1.5 meters. So now, what's the spring? Yep. So we've got 1/3 times 40 newtons per meter. So if we have n springs in a chain, what would the effective spring stiffness be? It'd just be 1/n times the spring stiffness for 1 spring. Okay, try this one. You have a single spring that has a stiffness of 20 newtons per meter. You put 4 of them together to make a longer spring. What's the effective stiffness of this long chain of springs? Okay, it looks like you nailed it. So we have the majority said, the big majority said 2, which is the right answer. So if we have 4 springs in series, you hang a mass on the end of it, it stretches 4 times as much as a single spring would. So the stiffness is only 1/4 as great as a single spring. So in fact, 5 newtons per meter is correct. Good job. So now we know how to deal with one of these chains of springs that we've got here. We know that if we measure the stretch of a wire, if we can figure out how many atoms there are stacked vertically in the wire, then we could figure out the stiffness, of one of those. But what we don't know what to do with is the fact that we've got more than one chain parallel to each other. And so the question indeed, Seth, is do parallel springs operate the same way? So let's think about parallel springs. So again, we've got our our spring here that has some length L0, and we hang a mass from it, and it stretches a stretch S. Now we put two of these springs side by side, and we hang the mass from both of them. But now each spring is only supporting half the weight. So each spring is only going to stretch half as much. So what's the spring stiffness here? The effective springs, what are we going to say about the effective spring stiffness? If the stretch is half as much, so let's go, yeah, exactly, that's right. So it's effectively is 2 times the spring stiffness for one spring. It's twice as stiff. And the more springs we put together, that's going to be the same, so that we'd say for n springs, in parallel is equal to n times the spring stiffness for one spring. There are some similar mathematical relationships in circuits, and we'll talk about those next semester. Okay, so let's see if we can answer a question about springs in parallel here. We have one spring stretches 0.4 meters if you hang 1 kilogram mass from it, but now you hang it from 2 identical springs. So how much does this parallel system stretch? Okay, great job. You're on top of it. So now that each spring has to support only half of the mass, each spring only stretches half as much, and so the total stretch of this object is half as much. And that means what in this case? We have a spring with a stiffness of 20 newtons per meter, and you put 4 of them side by side in parallel. What's the stiffness of this parallel array of 4 springs? So Michael's question is, I mean, by twice the size, I assume you mean twice the radius. I'm not sure how the radius of a spring is related to its stiffness. The stiffness of a particular spring is its own thing, so I'm not sure that's a relationship. What you said was, most of you said that the spring stiffness is 80 newtons per meter, which is the correct answer indeed, because for springs in parallel, each of them only has to support 1/4 of the weight, so they're not stretching as much, and so therefore, remember we said the effective spring stiffness for springs in parallel was n times the spring stiffness of one spring. so it's much stiffer. So now what we need to do is relate this back to the original problem, which was to stretch a wire, hang a mass on a wire, stretch it, and from that get information, actually extract the spring stiffness of a single chemical bond modeled as a spring in our system. So what we're going to consider here is a copper wire. And we already know the length of a bond here. We calculated that earlier. It's going to have a square cross. Just to make our life simple, we'll make it with a square cross section. So it's a square wire. Now, what does cross section mean? Well, if it means that if you cut into some three-dimensional object here, so suppose we saw this wire in half here, we make a cut through it. This is the cross-sectional area. Okay. Okay, so Michael's question is, would these? Oh, I see. Well, I think we're getting to an answer to you. I mean, I think you're trying to combine these things, which is what we'd have to do. So if Michael, if you're asking a question about what if you have we have two chains of two springs holding up some mass, and we want the effective spring stiffness of this. These are all identical springs. So each of these chains would be half as stiff, but we'd have two of them, which would make it twice as stiff. So is the original K sub S times a half for the series times 2 for the parallel, which does indeed give you the same effective spring stiffness. So that's the game we're going to be playing here and talking about chains of atoms. Okay, so it's going to be 1 millimeter on a side. So this is going to be 1 millimeter. And it's going to be 2 meters long. And what we're going to do with this wire here is we're going to take this wire, we're going to hang a 10 kilogram weight on it. We find that it stretches 1.67 millimeters. Okay, so we can pretend so this wire, which we know has got lots of long chains of multiple chemical bonds in series, but then parallel to each other, has so everything inside those bonds have their own stiffness, but what we're going to do is just the effective spring stiffness of this wire is going to be so we have K sub S effective times the stretch is mg, so the effective string stiffness is 10 kilograms times 9.8 newtons per kilogram divided by the stretch, which is 1.67 times 10 to the minus 3 meters. And that gives us an effective stiffness for the whole wire of 5.87 times 10 to the 4th newtons per meter. So wires are pretty stiff. So all we need to do is figure out how many parallel chains we have and how many in series in each chain, and then we'd have our answer. So the number of parallel chains we can get from taking this cross-sectional area of the end of the wire here. So here's our wire. We've got here's the end of the wire, and we have some number of atoms in an array in it. And so what we've done is we're looking, it's this picture here, okay? So this is the cross-sectional area A. The wire, we're going to figure out how many atoms there are there, because that'll tell us the number of parallel chains. So that's just number of parallel chains is just equal to the cross-sectional area of the wire over the area of one atom. And so that's equal to 1 millimeter squared. So it's 1 times 10 to the minus 6 square meters. And the cross-sectional area of one atom is just equal to the number we got for the atomic diameter squared. Again, remember each atom is taking up sort of a cubical area. So that's 2.28 times 10 to the minus 10th meters squared. So that's 5.20 times 10 to the minus 20th, I think. And that gives us a number of 1.92 times 10 to the 13 parallel chains. And number of bonds in one chain is just going to be the length of the wire over the diameter of an atom. So that's 2 meters divided by 2.28 times 10 to the minus 10 meters. And so that's 8.77 times 10 to the 9th in series. And so from our earlier work, we see that the effective spring stiffness of the whole wire is equal to this interatomic spring stiffness, the thing we're interested in, times the more chains there are, the stiffer it is. So it's times the number of chains, and it's divided by the number of atoms per chain. And this is our unknown. So we want the interatomic spring stiffness is the effective spring stiffness of the wire times the number of atoms per chain divided by the number of chains. So that is whatever we got for the effective spring stiffness here, 5.87 times 10 to the 4th newtons per meter times the number of atoms per chain, which was our 8.77 times 10 to the 9th, divided by the number of chains, 1.92 times 10 to the 13th. And so it turns out that this intereffective spring stiffness comes out to about 26.8 newtons per meter, so around 27 newtons per meter. So it's kind of an ordinary number, and that's the stiffness of a chemical bond here, modeled as a spring. And that's a reasonable number for atoms in a solid. The chemical bonds in diatomic molecules, for example, are actually stronger, so they're stiffer. But this is actually a pretty reasonable number for a solid. So, a triumph of microscopic reasoning. Just by reasoning about springs, we actually have been able to model the stiffness of a chemical bond, modeled as a spring connecting two atoms. And these are what are responsible for compression and tension forces. And we're out of time, but next time we will briefly relate this to a macroscopic measurement that we can make that's called Young's modulus. And then we'll talk about how this relates to things like not only just compression forces, but also things like friction. So that's it for this time.